Hello, good morning, ladies and gentlemen. My name is Pedro Oliveira, and today I'm going to talk about the mechanical behavior and microstructural evolution of a copper chromo zircon alloy at cryogenic temperature and in situ synchrotron X-ray evaluation. This is the list of all the authors of this work, and this is a little about me. I am a materials engineer. I have also my master in engineering and materials science, and actually I'm doing my PhD in materials science and engineering. This is the structure of this work. First, I'm going to give you a brief introduction. After that, I'm going to talk about the experimental procedure. After that, I'm going to talk about the results. And finally, I'm going to talk about the conclusions. The copper chromo zircon alloys have many important applications in the industry, but today the most important application for this alloy is in the construction of heat extraction components to work in the International Thermonuclear Experimental Reactor. In this application, this alloy has to present high mechanical resistance at cryogenic temperature. So, in this context, there are there are numerous studies in the literature addressing the complex relationship between microstructure and tensile properties of copper-based alloy, but few of these studies are concerned in the mechanical response at cryogenic temperature. And furthermore, for the best of our knowledge, there is no study evaluating the evolution of dislocations, stacking fault densities, and crystal size as a function of the formation degree. In this sense, the general objective of this work was to evaluate the mechanical response of a copper chromo zircon alloy at cryogenic temperature. Now, talking about the experimental procedure, this is the chemical composition of the alloy used in this work. We also tried to evaluate the effect of the precipitates on the tensile deformation at room and cryogenic temperature. For this, we worked with the alloy in three different heat treatment conditions. The first condition, the alloy was submitted to a solution heat treatment at 1273 Kelvin for 1 hour, which I'm going to call solid condition. The second condition, the alloy was submitted to a aging heat treatment at 723 Kelvin for 2 hours, which I'm going to call 723 condition. And the third condition, the alloy was submitted to another aging heat treatment condition, but at 773 Kelvin for 1.5 hours, which I'm going to call 773 condition. We performed our microstructure characterization using optical microscopy, scanning electron microscopy, and transmission electrical microscopy. Our in situ tensor test was performed in a global thermomechanical simulator integrated in the synchrotron radiation beamline, and the tensile test was performed at 123 Kelvin, which I'm going to call cryogenic temperature, and 298 Kelvin, which I'm going to call room temperature. The in situ tensile tests were performed using a XTMX station located at Brazilian Synchrotron Light Laboratory at Campinas, Brazil, and it is the only place in the world where you can find a global machine integrated to a synchrotron radiation beamline, and you can perform X-ray diffraction during the tensile test. This is some images of the global machine integrated to a synchrotron beamline. This is the chamber where you sample, and this is the X-ray detector. So during the tensile test, the X-ray coming from the synchrotron light source hits the sample, and the X-ray come out of the sample are detected by this detector. Here is an image with some details. Here is the jaws of the global thermomechanical simulator. This is where the thermocouple were placed in the sample, and this is the sample. Here is the sample of the tensile test, and this is the region where we perform the X-ray diffraction analysis. And these are the X-ray parameters used, where I can highlight that Each X-ray diffraction pattern were collected at each 4 seconds in a 2 theta interval of 60 degrees to 105 degrees. After that, the position and intensity of the diffraction patterns were corrected using this function. And after that, we used the modified Williamson-Hall method to calculate the dislocation density, crystalline size, and stacking fold density for each level of deformation during the tensile test. Now, talking about the results, the alloy presented chromium-rich particles even after the solution heat treatment, which is due to the low solubility of chromium in the copper matrix. And these particles also remain in the alloy even after the two different agent heat treatment. And this is the particle size distribution of those chromium-rich particles, which presented the average diameter close to 500 nanometers. Those insoluble particles were also confirmed by TEM analysis with the aid of the EDS and selected area diffraction analysis. And the alloy in the salt condition also presented some small GP zones which were also rich in chromium. And for the alloy after the heat treatment with the 722 condition, we also noted the presence of chromium precipitates. Here is precipitates, not particles, as before. And after the second heat treatment for the 772 condition, we also noted the presence of chromium precipitates. And here is the precipitate size distribution, where in the salt condition we also find the GP zones ranging up to 2 nanometers. For the condition 723, we found chromium precipitates with the average diameter close to 4.3 nanometers, and for the alloy in the 772 condition, we found chromium precipitate with the average diameter close to 6.6 diameter. So as we increase the temperature of the heat treatment, we found larger particles, large chromium precipitates. And here are the X-ray diffraction patterns obtained for the alloy tested at both temperature, where we collected a diffraction for each level of deformation ranging from yield stress to the ultimate tensile stress in all three conditions. And here is an illustration of the behavior of the X-ray diffraction pattern during the tensile test, where when the level of deformation increases, there is a decrease of intensity and increase in the full width of half maximum. And here is the stress strain curves, where we can see that from salt to 772 condition, there was an increase in the mechanical resistance, and this is due to the appearance and growth of the chromium precipitates. We also noted that the mechanical resistance is even higher for the test performed at cryogenic temperature, and this is due to the partial suppression of dynamic recovery. And we also noted that the test performed at cryogenic temperature presented a higher uniform elongation, and this is due to the activation of mechanical twinning as the main deformation mechanism operating at cryogenic temperature, and this mechanical twinning delays the necking of the tensile specimen. And this trend is confirmed here by the Cox-Max diagram, where we can see that the test performed at room temperature presented a higher dynamic recovery rate, and this is why the test performed at cryogenic temperature showing higher mechanical properties. And this is mechanical properties quantitatively, where we can see that from salt to 772 condition there was an increase in the yield stress and ultimate tensile strain, and this property was even higher for the test performed at cryogenic temperature, which is confirmed for the lower for the lower dynamic recovery rate at the cryogenic temperature. And here are the optical micrograph obtained in the tensile specimen near the neck region, where we can see a more pronounced presence of deformation twins in the test performed at cryogenic temperature, which is another indication that at this temperature, the deformation, the twinning deformation is the main deformation mechanism operating. We can also see a more pronounced presence of deformation twins now at both temperature, ranging from Sol to 773 condition, which could be an indication that the chromium precipitates act as nuclei for the appearance of deformation twins. And here we calculated the volume fraction of twinning grams, and these fractions increased from Sol to 773 condition, and this fraction was also higher for the test performed at cryogenic temperature. Again, this is a strong indication that at cryogenic temperature, the main deformation mechanism operating is the mechanical twin. Here I show you the stacking fold density as a function of the true plastic strength. For the test performed at room temperature, we can see that the stacking fold density has a slight tendency to decrease, but at cryogenic temperature, the stacking fold density uh, has a tendency to increase and and the final values of the stacking fold density here is higher than here. And so as the stacking fold density is directly related to the density of twins, we can infer that the higher is the stacking fold density, the higher is the density of twins. And we can see this here. We can see that for the test performed at cryogenic temperature, the density of twins tends to be higher than the density of twins of the test performed at room temperature. So this is another indication that at cryogenic temperature, the main deformation mechanism operating is the mechanical twinning. Here I show you the evolution of dislocation density as a function of two plastic strength at both temperatures, where we can see that at room temperature there is no significant change in the dislocation density, and this is due in the occurrence of the dynamic recovery, where the material reaches a balance between work hardening mechanism and softening mechanism. But at cryogenic temperature, the material has a pronounced effect of increasing of dislocation density. And this is another indication that at this temperature, there is a partial suppression of dynamic recovery. And here I show you the evolution of the crystalline size as a function of the true plastic strength, where we can see for both temperature that the crystalline size tends to decrease, but at cryogenic temperature, this tendency is more pronounced. This is not only one more evidence of the partial suppression of dynamic recovery, but this is all. But as the main deformation mechanism operating at this temperature is the mechanical twinning, the decrease in crystalline size is also an indication of the occurrence of the dynamic Hall patch effect, the same effect faced in the trip steels. Finally, the conclusion are the dynamic recovery rate was significantly reduced at cryogenic temperature compared to the room temperature. The highest strain hardening rate at cryogenic temperature for rigid conditions were mainly associated with the mechanical twinning. And the mechanical twinning is the main mechanism operating at cryogenic temperature. The precipitates interface act as nuclei for the stacking folds that promote twin effects, and mechanical twinning delayed the neck and contributed to simultaneously increase strength and plasticity as observed in twin steels. Thank you for your time and attention. And now, if you have any questions, I'll be glad to answer it.